if there's no questions or comments, we'll get started. So on Monday we looked at the plane equation, and let's just remind ourselves of that, and then today we'll move on to the line equation. So if we have our three-dimensional coordinate system, and if we have a plane somewhere in this three-dimensional coordinate system, first of all, remember that a plane is a flat surface, so I better make sure I draw straight edges. It's a flat surface, and even though I draw it that it's finite, it really is infinite. It goes forever in all directions, right? But I draw it like this. So a plane is a flat surface, and we define it with the plane equation, which is simply ax plus by plus cz is equal to d, where d is equal to a times x naught plus b times y naught plus c times z naught. And x naught, y naught, z naught are numbers that correspond to the coordinates of a particular point on the plane. Okay, that's what x naught, y naught, and z naught. And a, b, c are the components of what we call a normal vector. It's normal to the plane, so it makes a right angle with the surface of the plane. Okay, and we said that, so to write the plane equation, you just need two things. You need a point on the plane, any point on the plane will do, and you need a vector normal to the plane, and any normal vector will do, right? I could also equally use this vector, or I could use a normal vector over here, or I could use this normal vector, okay? Doesn't matter what size it is, it doesn't have to be a unit vector, and it doesn't matter whether it's pointing away from the top of the plane or the bottom of the plane. The beautiful thing is you can use any normal vector and any point on that plane, and you will get the same plane equation. Okay, so I just want to reiterate that a lot of times students will get confused and they'll think that this is the equation for a line. Just, like when we had y is equal to mx plus b is the equation of a line in 2D space. They think that, this is the equation for a line in 3D space. Not the case. This is the equation for a plane. But today we want to look at the equation for a line. What does it look like? Okay, well, in order to do that, let's first imagine that the line we're talking about in 3D space is actually the trajectory for a point that's traveling in a straight line. So let's say there's our straight line in 3D space. Okay, and let's say that we've got a particle that's traveling along this line, I don't know, maybe in this direction. Okay, at some particular point t in time, the particle traveling along this line will have coordinates. Let's say x of t, y of t, and z of t. Okay, and since the particle is moving along this line, these values will change as the particle moves, obviously, right? The coordinates that this particle is at as it travels along the line will be changing with time as the particle moves with time. So we make these coordinates functions of time, okay? The x function of time, the y function of time, the z function of time. And that in an essence, whatever these equations are, whatever these functions are, actually define a particular line, okay? So if all we have to do is come up with these equations, these three functions that give us the x, y, and z value of this particle as it travels along the line as a function of time. If we can do that, we've got basically a unique representation for this particular line in 3D space. Okay, so we call these parametric equations. We're going to be using those a lot in the first part of this course. And one place we use them is here in lines. Okay, we call them parametric equations because they're equations that describe x of t, y of t, and z of t using a parameter, and the parameter is t. So the parameter in parametric is t in this case. Now t doesn't have to be the parameter, it could be any other letter, but it's helpful to think of t as time in this case. Okay, so let's look at a particular example, and we're going to look at a couple of different methods for actually coming up with these parametric equations. Let's say we've got a line in 3D space, and we know that at a particular point in time, the particle traveling along this line is at coordinate q0. Let's say that's coordinates -1 to 2. And later on in time, the particle is at point q1, which has coordinates 1, 3, -1. Okay? At some time in between those 2 points, the particle might be, let's say, here. And let's say it's at some point which is a function of t time. Okay? We could say, well, let's say that at time t equal to 0, the point is at point q0. Okay, so when t is equal to 0, the particle's at this point. Let's say at some other time t equal to capital T, whatever it is, we'll say that the particle is at point q1. Okay, so this is when t is equal to 0. This is when t is equal to some time capital T. Okay, and at some arbitrary time in the middle, let's say at time t, the particle's just at point q of t. Okay. Okay, we're going to assume a constant velocity for this particle as it travels along this line. At time t equal to 0, it's here. At some other time t, it's here. And at time t equal to big T, it's here. But the entire time it has a constant velocity. Well, we can recall that velocity is just displacement over time, and we can use vectors to represent displacement. Okay, so for instance, the vector that points from q0 to q, okay, would be this vector here. Let's use a different color. This vector here, from q0 to q. Okay, well, we could say that vector is the displacement as the particle goes from q0 to q, and if we divide it by the time it takes to go over that displacement, we've got the velocity. Okay, well, what's the time? Well, this is time t equal to 0, and we said the particle is at this arbitrary point at a time t, just at a time t. So we just write t down here. Okay, small t minus 0 gives us small t. That's the time it takes from the particle to go from here to some arbitrary point here. That gives us the velocity. Well, if we assume the velocity is constant, we can also calculate the velocity if we displace from here to here. Okay, and that velocity, well, is from q0 to q1 divided by the time it takes to go that, which is capital T, right? Because at this point of the displacement, time is equal to 0. At this point, time is equal to capital T. So the difference is capital T. So those are two velocities, and if we assume the velocity is constant, that has to be equal. Okay? Okay, well, we just rearrange this a little bit. Q naught Q is equal to little t over big T, Q naught Q1. Okay, we know the coordinates for Q naught and Q naught and Q1. And let's just say that the coordinates at time Q, maybe I'll write it back up here. The coordinates at time Q here is just, or X, Y, and Z. Well, then the vector Q naught to Q is just X minus whatever Q -1. So we're just going to take these coordinates minus these coordinates give us this vector, right? which is this vector here. So we just write x minus -1 is x plus 1, y minus 2, and z minus 2. So we just formed this vector here, because we know the coordinates for q naught, and we, oh my goodness, it's not a z. Pardon me. No, it won't let me erase. Y minus 2. Okay, on the right hand side we've got t over big T, and we've got q naught to q1. So that vector again is simply the difference between these coordinates. These coordinates minus these coordinates give us this vector. And when you do that, you get 2, 1, negative 3. Okay. So now we've got an equation with what? Well, we've got one vector is equal to another vector, so that really gives us three equations. For two vectors to be equal, their corresponding x, y, and z components must be equal. So really we got three equations here. We got x plus 1 is equal to t over big T times 2. Okay? And we've got y minus 2 must be equal to little t over big T times 1. And z minus 2 must be equal to little t over big T times negative 3. Okay, so I can rewrite that. X plus, or actually, yeah, we'll do it this way. Okay, so we have our three parametric equations for this line. Okay, well, parametric equations are three equations. One has x in it, one has y, one has z, as well as the parameter, which in this case would be small t. Well, what about big T? What is this big T? Well, big T is a constant. Big T, all it is the time it takes to go from here to here. This is a fixed length, so obviously by making big T some value, we're making an assumption about what the velocity is of this particle. We haven't said what the velocity is, we've only said it's constant. Well, we could have any velocity we want as this particle moves along this line. It doesn't matter how fast the particle is moving, it's still moving along the same line. So we could choose any value of big T here to get the parametric equation for this line. Okay? We could, for instance, say, well, let's just make big T equal to 1. Well, in that case, if I rewrite these equations with big T equal to 1, I get x is equal to negative 1 plus 2t. And I get y is equal to 2 plus t, and I get z is equal to 2 minus 3t. Okay? If I assume big T is equal to 1 second, for instance. Well, I could also assume, and it's just as legitimate to assume that t is equal to maybe 0.5 seconds. Maybe the particle's actually moving twice as fast, okay? But still along the same line. Well, if I substitute 0.5 for big T into these parametric equations up here, I get x is equal to negative 1 plus 4t. I get y is equal to 2 plus 2t. And I get z is equal to 2 minus 6t. Okay? So, well, what's going on here? Why do I have 2? Well, I have 2 because I chose two different speeds for the particle as it moves along the same line. There's an infinite number of speeds the particle could be moving, and therefore there are an infinite number of parametric equations, different parametric equations. You'll note these are different, right? They're different parametric equations, but they all represent the same line. So the big takeaway here is the parametric equation for a line in 3D space is not unique. You can come up with an infinite number of parametric equations that could all represent the exact same line in 3D space. Okay, so there's an infinite number of solutions. All right, the other thing to note here is, let's talk about this parameter t. The parameter, in this case t, small t, does not have to represent time. It's very often convenient to think of it as time, especially when we're considering what the parametric equations of a line are, but it doesn't have to be. And it doesn't have to be t. It can be any letter representing anything. Or maybe it doesn't represent anything physical, okay? Okay, so that's one way we can come up with the parametric equations for a line. We just started knowing 2 points on the line, okay? Method 2. Wow, I was getting ahead of myself. There's 2 methods. That's method 1. Sorry about that. Let's look at method 2 quickly. Okay, we got the same line. Let's say, again, we know that there is a point, let's call it P0 with coordinates x0, y0, and z0 on the line. And sometime later, our particle that's moving along this line is at point P, which has coordinates x, y, z. Okay? And let's say we also know a vector that is parallel to this line. Let's call it V, with the components V1, V2, and V3. Okay, well, we can again draw a vector, say from P0 to P, where these coordinates x naught, y naught, z naught are known, and x, y, z are just arbitrary along the line. Okay, so P naught P would simply be equal to x minus, x naught I hat plus y minus y naught j hat plus z minus z naught k hat. I'm going to write it in that form just to get you used to writing vectors this way too. It's the same as writing it like this. Okay, so I'm going to alternate, throughout the course, I'm going to alternate between these 2 ways of writing vectors. They're both the same. Okay, well, that's the displacement vector as the particle goes from point P0 to P. Okay? Well, if we assume that this velocity, that this vector v here is the velocity vector corresponding to this particle moving like this, well, then we can just say, okay, pardon me, the displacement as that particle goes from P0 to P, which is represented by that vector, right, let's say in meters, is equal to some time in seconds times the velocity, meters per second, right? Units of this would be meters, units of this is seconds, units of this is meters per second. So meters equals meters. Okay, well, that gives us basically the exact same representation for this line as we had before. If we go back up to method 1 here, right here. With big T equal to 1, right? It's the exact same thing as we got up there. Okay, but we don't even have to think of v being velocity and t being time, like I said. Purely from a mathematical point of view, you can just say, well, we know that this vector v is parallel to the line. Therefore, you can think of, okay, well, I've got this vector here. I've also got this vector here. since this vector is parallel to this vector, they're really the same vector if they have the same magnitude. Now they don't necessarily have to have the same magnitude, but if I scale one by the appropriate value, it will have the same magnitude of the other, same direction, same vector. So I could just write, well, this vector p0 to p on my line can be made equal to the velocity, or to the vector v. It doesn't have to be velocity, this vector v, if I multiply v by the appropriate constant so that it has the same magnitude as the vector p naught p. And let's just call that constant, I don't know, k. Right? So I multiply this vector parallel to my line by the appropriate constant k, and it is now equal to this vector on the line from p naught to p. Okay, so this gives us our parametric equation again, right? We know these coordinates here, x naught, y naught, z naught, are actual numbers corresponding to a point on the plane. We've got this arbitrary point that could be anywhere with coordinates x, y, z. So again, you form this vector using those coordinates and you make it equal to these values here, and you end up with x is equal to x naught plus k times v1, y is equal to y naught plus k times v2, and z is equal to z naught plus k times v3. And these are the parametric equations for our line, and this is the form we most often use. Parametric. Okay, so if you're given the parametric equations for an actual line, these are going to be numbers, x, y naught, z, x naught, y naught, z naught. v1, v2, v3 are going to be numbers as well. K will just be k, and x, y, z will be x, y, z. Okay, so again, k here is our parameter. It can represent any physical quantity, or it doesn't have to represent any physical quantity. X naught, y naught, z naught is a particular point on the line. And v, which is equal to v1, v2, and v3, is a vector parallel to the line. Okay, there are infinite number of points on a line. There are also an infinite number of vectors parallel to that line. Therefore, there are an infinite number of parametric equations that you can write for the same line. Excuse me. Okay, sometimes we write this in its vector equation, and to do that I'm going to, all the way to the top, I don't want that. I'm going to go back to here. No, I'll just draw it again. If we draw our three-axis coordinate system, and here's our line. Let's say this is the point x naught, y naught, z naught. I'm going to draw what we call a position vector, and we're going to use these a lot in the next few lectures. So I'll introduce that here. A position vector is a vector that always starts at the origin of the coordinate system and it ends at the position of the point that it's defining. Okay, so a vector that goes from the origin to the point x naught, y naught, z naught, let's call that the position vector r naught. Okay, that's a vector r with sub naught indicating it's pointing to the position of point x naught, y naught, z naught. Okay, at some later time, maybe the particle is at this point with coordinates x, y, z. So the position vector for that point, again, starts at the origin and goes to there. Okay, so this one is this one, and this one, I'm just going to call it r, and I'm going to make it a function of k. Okay, because if I go back to this this diagram up here, given the parametric equations, k has k has one value when the point is here. K has a different value when the point is here, right? It's as the parameter k changes, my position or my point on this line changes. That's what these parametric equations tell us, right? If you look at here, the value x, y, z is equal to these initial values plus k times some other number, okay? So as k changes, x, y, z are going to change. When k has one value, say when k is equal to 0, x, y, z have the values x naught, y naught, z naught. When k is equal to 1, then x, y, z have the values of x naught plus v1, y naught plus v2, and z naught plus v3. So as k changes, x, y, z change, okay? So that's why I write this position vector that is defining the position of point x, y, z along my line as a function of k. K changes in this position vector. So a little bit later, k is going to look like this, if k represents time, okay? As k changes, my position vector is going to change. Okay, when k is equal to 0, this is the position vector. When k is equal to some other bigger value, k is equal to this. When it's even bigger, k is equal to that, for instance. So now we can write our vector equation for our line. Okay, rk will always, the tip of the arrow of that position vector will always be along the line, and it's equal to my initial position vector when k is equal to 0, plus k times this parallel vector. Right, this parallel vector, I originally drew it down here, maybe like that, but it's a free vector, so that means I can move it around, and I can draw it up here like this. Right, where this one is k times v. And so you can see, well, we've got three vectors here. We've got this vector is the sum of this vector and this vector, right? This vector, which is our r of k, it's the vector that, the position vector, which is going to be tracing out a straight line with the tip of its arrow as k changes, is equal to this vector, which is r0, the one that points at this stationary point here, plus this vector. So as k gets bigger, this vector is going to grow in this direction, which means this vector, which defines the line, also moves like this, and then like this, and then like this. Okay, so it's just these three vectors. It's just vector addition that we're doing here. So sometimes you see this as the vector equation for the line. But if you break it out for three-dimensional vectors, pardon me, we've got three parametric equations, these same three parametric equations up here. Okay, so it's really the same thing as this, it's just written more conveniently in vector notation. So, any questions about the equation for a line? We'll do some examples here in a minute, but any questions about what we've got so far? Okay, so just like a plane equation, to write the plane equation, you need two pieces of information. You need a point on the plane, and you need a vector perpendicular to the plane. To write the equation for a line in 3D space, you also need only two pieces of information. You need a point on the line, which is x naught, y naught, z naught here. It could be any point on that line. Pardon me. Okay, so the first piece of information we need is a point on the line. Any point will do. And that's represented by x naught, y naught, z naught. The second piece of information we need is a vector parallel to the line. It doesn't have to be on the line, it just has to be parallel to the line. It can be on the line, which would automatically make it parallel to the line, but it doesn't have to be, okay? But it has to be parallel. And v1, v2, v3 here represent the vector that's parallel to the line. So if we have those two pieces of information, we right away can just write down the parametric equations for that line. Conversely, if you're given the equation for a line, right away you know two pieces of information. You know a point on the line, and you know a vector parallel to the line. Okay? And all the equations, or all the questions or problems we can give you about lines, it's one or the other. It's, you know, find the equation for the line if we give you some information, or here's the equation for a line, do something else, and you have to use this information you're given. Okay? It's one or the other. That's all it is. Okay. We talked about k, the parameter, and we talked about that. Good. Okay, let's look at some examples. And at the end of this lecture, there's a number of different problem types that are listed. You know, if we give you this, find this. If we give you that, find this. Okay? You can look at those and think about what would your strategy be. But let's look at some examples first. And the first one's pretty easy. Find the parametric equation for the line that passes through 2 points. Point P, which is -3 to -3, and point Q, which is 1, -1, 4. Okay, find the parametric equation for the line that passes through point P and point Q, and we're given the coordinates for P and Q. Let me ask you first, is there only one line that passes through those 2 points? Anybody want to guess? Got a 50-50 chance. Is there only one line that passes through points P and Q? Somebody give me a yes or a no. Anyone? Unmute and just say yes or no. You got a 50-50 chance. Is there only one line that goes through those 2 points? Okay, everybody's shy. Yes, there's only one line that goes through those 2 points, right? If you have 2 points, 2 specific points in space, there's only one straight line that'll pass through both of them, right? There's an infinite number of lines that pass through 1 point, but there's only one line that passes through 2 points. So that's fine. Now, there are an infinite number of parametric equations that can be written to describe that line, but there's only one line. Okay, so don't get those two things confused. Okay, well, we need 2 pieces of information to write the parametric equation of a line. We need a point on the line. Well, we're lucky we've got 2. We can pick either one. We need a vector parallel to the line. Okay, so how are we going to get a vector parallel to the line? The only 2 things we're given are these 2 coordinates, P, Q, on the line. Well, pretty much the only thing we can do is we could draw a vector between P and Q, and that vector would be parallel to the line, right? It's on the line. It's got to be parallel to the line. Or we could draw a vector from Q to P. That would work too, okay? Vector parallel to the line. Okay, well, let's just use P to Q. Okay, so I'm going to draw it as the difference between 2 position vectors. Note those are vectors. I used the angle brackets, so those are vectors. Okay, we introduced the notion of a position vector, so presumably somewhere there's going to be an origin. Let's say the origin of our coordinate system is right here. Okay, so we can have a position vector that points to point P. We can have a position vector that points to point Q. Okay, if I call this vector here the position vector for point P, and the position vector for point Q looks like this. And this vector here is obviously P to Q. Okay, well, the position vector for Q is equal to the sum of P plus PQ, so PQ has to be equal to Q minus P. Okay? So this is a position vector Q, this is the position vector for P. So I can write PQ as the difference between two position vectors. It's the same thing though, we get the exact same thing if we use coordinates though, right? Okay, so now we need a point on the line. I don't know, let's pick point P. We got two choices, P or Q. We can use either one, they're both valid. If we pick point P, now we just have to write our parametric equations. And we remember the form is just x is equal to x naught plus kv. 1, y naught kv2, z is equal to z naught kv3. Okay, so our parametric equations are x, y, z are equal to x naught, y naught, z naught are the coordinates on of the point on the line. If we're picking point P, well, P has the coordinates of -3, 2, -3, -3, 2, -3, our x naught, y naught, z naught. And then we just need v1, v2, v3, which is our vector PQ, we can call it V, and that was equal to, we never wrote it out, it's 4, -3, 7. So the coefficients for K here are V1, V2, V3 are 4, -3, and 7. So we got plus 4 times K minus 3 times K plus 7 times K. Okay? Or we could pick point Q, in which case we would get x is equal to, x naught for point Q is 1, y is equal to -1, z is equal to 4. Those are x naught, y naught, z naught for point Q. And we could use the same vector, so it would be plus 4k minus 3k plus 7k. Okay, also valid as the parametric equations for that line. Okay, any questions about that simple example? Okay. Those are pretty simple. You know, if you're working as an engineer, nobody's ever going to ask you probably to write the parametric equations for a line. However, depending on what kind of engineer you're doing and what your work is, somebody might ask you what the perpendicular distance is between a point and a line, right? So let's look at an example like that. It's a little bit more practical. Find the perpendicular distance from point S, which has coordinates 1, 1, 5, to the line x is equal to 1 plus t, y is equal to 3 minus t, and z is equal to 2t. Okay, so we're given the parametric equation for a line. The three parametric equations for a line. Okay, well, as I said in my last lecture, whenever you're doing a problem, if you're not given a diagram, I highly recommend you sketch one. Okay? Doesn't have to be to scale. You don't have to figure out exactly what this line looks like in 3 dimensions. Just draw a line. Oops. Okay, here's my line. And we we right away, and we got a point S. Okay, well, let's just say point S is up here. I could draw it anywhere. Again, I didn't draw a coordinate system, so we don't have to do anything to scale here. Okay, I'm looking for the perpendicular distance from that point to the line, which is obviously this distance here, right? It's not going to be that distance. That's not the perpendicular distance. It's this distance here, which would be the shortest distance between this point and this line in 3D space. So we're looking for this distance. Okay, well, we're given the parametric equation for the line. Let's write it like this. So right away we know two pieces of information. We know a point on the line, x naught, y naught, z naught, which in this case are 1, 3, 0. So I don't know, that point is somewhere on the line, let's just put it there. Okay, let's call that point P with coordinates 1, 3, 0. We also know a vector parallel to this line. Let's draw it like that, where the components of v are just the coefficients of our parameter t, which are going to be +1, -1, and +2. Okay, that's a vector parallel to the line. So now we got all the information that we're given in our diagram. Okay. All right, we're looking for this distance. And like a lot of these problems, there's more than one way to do this. So I think in the lecture notes we show you 4 different methods. I'll show you at least a couple. The rest you can look at yourself if you're interested. Method 1. Well, we're going to make use of the dot product. Okay, so in this course, a lot of the problems you're going to have to combine all the tools that you've learned. Okay? Don't expect that the only time you're going to use a dot product is when we ask you find the dot product of 2 vectors. Okay, that's a high school level question. We're not going to ask you that. We're going to ask you other questions that are more complicated that you're going to have to use all of these tools. So in method 1, we're going to make use of the dot product. Okay, first of all, we're going to do that, we need some vectors, right? If we're going to take the dot product, you need at least 2 vectors to do the dot product. Well, I only see one vector here, vector v, but we got 2 points identified in space. We could draw a vector between them. Call it PS. Okay? So PS is going to be equal to the position vector for point S, which is 1 minus 0, 1 minus 0, 5 minus 0. That's the position vector for the point S, minus the position vector for point P, which is going to be 1, 3, 0, which gives us 0, -2, 5. Okay, so we've got a vector PS. And we've got this vector V. Okay, well, we can see that we've got a right angle triangle here, where the side, or the distance we're looking for is the length of one of the sides of the triangle. So maybe we could just use some basic trig here. We know this length. It's obviously the magnitude of this vector. Maybe we can make use of that to find this length. Well, we don't know any angles here other than it's a right angle triangle. We don't know this length or this length. So how are we going to get one of these lengths? Well, we have a second vector here, v, which is parallel to this line. So which means we could move v over like this, right? V could be on the line as long as it's the same direction, which it is if it's parallel, and the same magnitude, same vector. Now we could find the projection of this vector onto this vector here, this v vector. Okay? Maybe I'll draw the v vector down here like this instead. Again, it's still parallel. It's still parallel to the original v vector I drew, and it's got the same magnitude, so it's the same vector. So now I could simply use projection to find the projection of this vector onto this vector, which would obviously give me, let's use a different color, let's use blue for the shadow, which would give me this length here, right? That would be the shadow. That would be the shadow thrown onto this V vector by a light source up here shining straight down on the vector PS. Okay, so we're looking for the projection of PS onto the line V. V is a vector, but it's on the line. Okay, well that projection is equal to PS dot, we're making use of the dot product, V hat. Remember that in a projection, the second vector has to be a unit vector. Now, if I want an actual vector, I have to multiply it by V hat again, right? This dot product gives me a scalar, gives me this length, and that's really all you need, but let's just keep using vectors. Whereas when I multiply it by V hat is a unit vector pointing in this direction. It gives me the direction, which then turns this into a vector. Okay, so that's my projection vector. Okay, well, we need V hat. Well, we've got V, so V hat is simply equal to V divided by the magnitude of V. We've got V, it's 1, negative 1, 2. So 1, negative 1, 2, and the magnitude of that is 1 squared plus 1 squared plus 2 squared. 1 plus 1 plus 4 is 6, square root of 6. Okay, so that's our V hat vector. Okay, so if I take PS dot V hat, that's just the length of the projection vector, that distance I'm looking for, or at least part of the distance of one side of the triangle. So PS we said was 0, negative 2, 5. Take the dot product with V hat, which is 1, negative 1, 2 over root 6. And when you take that dot product, you get a scalar. It's 12 over root 6. Okay, so that's the length of the projection vector. It's this distance here, this blue distance. It's the distance of one side of my triangle. Okay, well, you can just use basic geometry now. You got the length of the hypotenuse. You just find the magnitude of PS. That gives you the length of the hypotenuse. You got this length. You use Pythagorean theorem. You got this length, right? Or we'll just keep using vectors and be a little bit more mathematical about it. We call this projection vector P perpendicular. Pardon me, not P perpendicular, P parallel. Because it's parallel to the line. We would call this one P perpendicular. And it's the length of P perpendicular that we're looking for. We've got PS, we've got P parallel. We need P perpendicular. Right, and I'm going to just, to make it really clear, let's use a different color of red. Right, this vector looks like this. So obviously PS is equal to P parallel plus P perpendicular. So P perpendicular is PS minus P parallel. Oops, which is equal to PS we said was 0, negative 2, 5. And P parallel is simply this magnitude times this. This is V hat, right? Which gives, we're just doing this here. This 12 over root 6 is the result of the dot product. You multiply it by V hat, and that gives us P. Oh, I'm sorry, I'm starting to mix. Let's take away that S, keep things the same. And we're looking for P parallel, that's this guy here. So when you multiply those two out, you get 2, negative 2, 4, right? That's just this times this. (12) divided by 6 is 2. 2 times this vector gives us this. Okay, and that gives us -2, 0, 1. Therefore, the distance is equal to the absolute value of that perpendicular vector that we just found, which is √5. Okay, so that's one method, and we got to stop there. We're done. We'll look at a couple other methods the next day, as well as a few more examples. Any questions before we go? All right, we'll continue on with this on Friday. Have a good couple of days, anyone. I'll hang around for a minute if anybody has any questions.